All right, today's lesson, we're going to look at the mean value theorem and also a specific case of the mean value theorem, which is called Rolle's theorem. So you have some conditions. Just like with intermediate value theorem, there's going to be some conditions that have to be true, and then we'll be able to state a conclusion based off of those conditions. All right, so your conditions are if the function is continuous on a closed interval, a to b. Okay, I'm going to write closed interval. And it's differentiable on an open interval. All right, so continuity has to be true at the endpoints. Differentiability only has to be true inside the interval, not necessarily at the endpoints. Then there is at least one number, c, in a to b, such that. Okay, so we're going to draw a picture, and then I will tell you about the conclusion. Okay, so if you have a function f, okay, and we're going to have some endpoints on this function. All right, so we have a function f. This is a, this is b. All right, and this is f of x. All right, and so anytime you have a function with some endpoints, you can find an average rate of change. Let me draw that a little better. So I'm trying to draw just a line between these two. All right, and so the slope of this line would be f of b minus f of a over b minus a. It's the average rate of change between those 2 points. Okay, and so what this is saying is that there is at least one place which we can label with the letter C that's in A to B, so it's in between these two. Okay, so I'm going to say it's maybe right about here. This is C, where the slope of the tangent line is equal to the slope of the average rate of change. All right, and so that is our conclusion. So our conclusion is that f prime of c, that's the slope of the tangent line. All right, let me write that over here. Slope f prime of c. All right, where the slope of the tangent line is equal to the average rate of change, f of b minus f of a over b minus a. All right, so two other ways to write the conclusion. You could say in words, slope of the tangent equals slope of the secant line. I probably should include the word line there too. All right, or you can say the instantaneous rate of change equals the average rate of change. So any of those three versions are acceptable. We are going to be mainly using the top version of this. All right. So a special case of the mean value theorem is called Rolle's theorem. Personally, I never use Rolle's theorem because I always just use mean value theorem because we can just use the regular mean value theorem even on this problem. All right, this is an interesting case. So you'll see the continuity on the closed interval. You see the differentiability on the open interval. There's a third condition now. F of A is equal to F of B. Okay, so if I drew my picture over here, I could have like A and then B like this. All right, then my function could do something in between those like that. All right, but they're equal. And so when I do my average rate of change, my slope is 0 because it's a horizontal line. And then what that means is that somewhere on this interval in between A and B, there's a C value where the tangent line is also horizontal. So now instead of doing f of b minus f of a over b minus a, we can just say that f prime of c is equal to 0. All right, and then we could say is there is a horizontal tangent at C. All right, so there is a horizontal tangent line at x equals c, and then there's not really three ways on this one, but just so we can fill in the blank here, slope of tangent line at C is 0. All right, so again, Rolle's theorem is a special case of the mean value theorem. If f of A and f of B are the same value, then f of A minus f of B would be 0. You get a 0 on top of that average rate of change. All right, so I'm going to write that over here actually. If f of A equals f of B, then f of B minus f of A over B minus A is equal to 0. Subtracting two things that are the same number will give you a 0 on top. You will not have a 0 on bottom because A and B are different values. And so that fraction will be equal to 0 there. All right. Show that the conditions of Rolle's theorem are met and find the C that Rolle's theorem guarantees. So this problem does specifically mention Rolle's theorem. So we are going to solve it as a Rolle's theorem problem. Although I've never seen a question on the AP exam that mentions Rolle's theorem by name. Okay, it will usually say, must there exist a value, blah, 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 something like that. And then you get to pick what theorem you want to do. And they want to see that you're picking the correct theorem because we have intermediate value theorem that we've learned about. Now we know about mean value theorem and Rolle's theorem. And they want to make sure that you're picking the correct theorem. So that's part of the question. So they're not going to tell you which way. Right? We are going to do it with Rolle's theorem because this question mentions it, and it's good to practice each one individually so that you know what to do when the question pops up later on. All right, so the conditions of Rolle's theorem are that the function must be continuous on a closed interval. That's the first condition at least. So we're going to write that down. We want to say how we know that the function is continuous. So f of x is a polynomial which is continuous everywhere. All right, since it's continuous everywhere, then that implies it's continuous on this specific interval. All right, number 2, f of x must be differentiable. So we are going to take the derivative of this. F prime of x is equal to 2x minus 1. All right, f prime of x is linear, which is continuous everywhere, which is, let's say, defined, not continuous. So since f prime is defined everywhere, f of x is differentiable. Everywhere. All right, and then for Rolle's theorem, we have to do number 3, that f of a, so that's f of negative 2. Okay, we're going to work this out. That's 4 plus 2 minus 6, which is equal to 0. And then f of 3, which is 9 minus 3 minus 6, which is 0. So f of negative 2 is equal to f of 3. All right, once we have stated all of the conditions, then that means we can apply Rolle's theorem. So we're going to do our therefore Rolle's theorem applies. All right, and then we can finish our conclusion. Usually with intermediate value theorem, we'd be done. That would be our conclusion that IVT applies. Okay, but here we can say that Rolle's theorem applies, but then we still have to say the conclusion. We still have to say that f prime of c is equal to 0. All right, so therefore Rolle's theorem applies and f prime of c is equal to 0. All right, and then this says we have to find the c value that Rolle's theorem guarantees. So we're actually going to find this value. F prime is 2x minus 1. F prime of c is 2c minus 1, and that's equal to 0. So c is equal to add 1, divide by 2, c is equal to 1/2. Make sure the c you find is inside the interval that you were given. It is. So that is our answer. All right, on the back. So given the function this on the interval from 1 to 5, the graph of f of x is shown on the right. Visually, what is MVT trying to find? Draw it in. Okay, so mean value theorem is trying to find that if we were to graph the point at x equals 1 and graph the point at 2, 3, 4, x equals 5, and draw a line between those, that's the average rate of change. And so MVT is trying to find the point along this curve where the slope of the tangent line is the same as the slope of the secant line. All right, so that's visually what we're trying to see. All right, so we've done that over here. All right, B, show that the mean value theorem applies and find the C value that the theorem guarantees. Okay, so this one's a little trickier on the conditions. Number one, we have to state that f of x is continuous. Now, f of x is not always continuous. All right, so this function is discontinuous at x equals 0. That would give us a 0 in the denominator. Okay, but 0 is not in our interval. We have an interval from 1 to 5. So we're going to state that, what we just said. So f of x is discontinuous at x equals 0 only. So f of x is continuous on 1 to 5. All right, second, differentiable. So we're going to take the derivative of our function, f prime of x is equal to, derivative of 3 is 0, and then remember that you can rewrite this. I'm going to rewrite the whole function up here. F of x is equal to 3 minus 5x to the negative 1 power. So we're going to multiply by negative 1, we're going to get positive 5. And then this becomes x to the negative 2 as we subtract 1, and that's going to go back down on the bottom. So it's 5 over x squared. All right, f prime of x is undefined at x equals 0 only. So f of x is differentiable on the open interval 1 to 5. All right, so remember when you're doing mean value theorem, those are the only two conditions. So once we have stated that, we can say, therefore, MVT applies. And then we have to find the C value that this guarantees. So we're going to do f of C, which is 5 over C squared, is equal to, then we're doing the average rate of change on this interval. So we're doing f of 5 minus f of 1 divided by 5 minus 1. All right, so that's going to be 5 over C squared is equal to, okay, f of 5 is going to be the y value of this point right here. So it looks like that's a 2. Minus f of 1 is going to be the y value of this point. Looks like that's a negative 2. Divided by 5 minus 1 is 4. That's a 4 on top and a 4 on bottom. So this is 5 over C squared is equal to 1. So we get 5 is equal to C squared multiplied by the denominator. And so we get C is equal to plus or minus square root of 5. But remember that our answer has to be inside the interval, 1 to 5. So we can't have a negative number as our answer. So C is equal to the square root of 5. And let's verify, square root of 5 is a little bit bigger than 2. So 1, 2, and a little bit. And yeah, that looks like that's that point right about there. So it seems like that makes sense. All right, I use the graph to find my y values, but we could have also plugged those numbers into the function. If I plug in 5, 5 over 5 is 1. 3 minus 1 is 2. If I plug in 1, I get 3 minus 5, which is negative 2. All right. Last example is going to be more of a real world example. So you're driving a car, traveling on an interstate highway at 50 miles per hour, and you pass a police car. 4 minutes later, you pass a second police car, and you're again traveling at 50 miles per hour. The speed limit on the interstate is 60 miles per hour. The distance between the two police cars is 5 miles. The patrolman of the second police car gives you a speeding ticket for driving 75 miles per hour. How can he prove that you were speeding? Okay, so this is a mean value theorem question. So number one, we are talking about speed. And so speed is a continuous function. So that's kind of like a polynomial. We know that polynomials are always continuous. We know that speed is continuous. All right, number 2, speed is also differentiable. If you take the derivative of speed, you get acceleration. And acceleration is always defined, and so speed is also a differentiable function. Okay, these are things that you know, or in problems on the actual test, they'll give you a function for speed, a function for position, and all that. So you'll be able to use what we did on the last problem as well. All right, so since speed is continuous and speed is differentiable, we can say that therefore the mean value theorem applies. All right, I'm going to backtrack just for a minute. So I need to rewrite this a little differently. Speed is the result of what we're doing, and we're actually looking at a different function when we are finding the speed. Speed is our rate of change. Okay, so instead of writing it this way, right, what we're going to be looking at actually is the distance. So the distance between the two police cars is 5 miles. Okay, and then they told us how long it took us to make that, 4 minutes later. Okay, so what we're actually doing is we're talking about the distance function. And if you think about driving a car, the distance you drive is continuous. Okay, because remember, for us to be discontinuous, we have to have an asymptote or a hole or a jump. And if you're driving, your distance doesn't ever jump to some other value. It doesn't have an asymptote and go to infinity. It doesn't have just a hole where you skip over a number. Okay, when you're driving, you're starting at one distance and you're going to another distance continuously. Okay, so what I want to say here instead is distance is continuous. All right, and then if you take the derivative of distance, you get speed. And speed, just the same way. You're not going to jump speeds, right? You're going to go from 0 to whatever miles per hour back down to 0, and that's a continuous function as well. So since speed is continuous and defined, distance is differentiable. All right, so now that we've got that correct, now we can do our problem. So what this says is that the instantaneous speed is equal to the average speed. All right, so when we're given a speeding ticket, the officer is saying that we were going 75 miles per hour at some point. Now, according to their radar gun, we were going 50, and then 4 minutes later, we were going 50 again. So the officer is having to prove, like, I clocked you at 50 2 times. How do I know you were going 75? Well, because mean value theorem says that instantaneous speed is equal to average speed. So in this case, instantaneous speed is equal to, all right, so average speed is distance divided by time. So distance is 5 miles. And then time is 4 minutes. Now, we want this in miles per hour, not miles per minute. So we need to convert 4 minutes into an hour. Okay, so if you have 4 minutes, then you multiply by, we want to cancel minutes. So we have minutes down here, and we put hours up here. So 1 hour is equal to 60 minutes. So minutes cancel. That'll leave us with hours. 4 divided by 60 is 1/15. And that's in hours. And now we have our average speed in terms of miles per hour. All right, so you multiply by the reciprocal. 5 times 15 is equal to 75 miles per hour. And there it is. So we're done with this one. Okay, so they can prove that we had to have been going. The instantaneous speed had to have equaled the average speed at some point in that interval. And so therefore, since our average speed was 75, we must have been traveling 75 miles per hour at least during those 4 minutes. All right, so now you are going to be foolish and you're going to argue with the patrolman who's writing your speeding ticket. He's going to call his brother who's currently taking calculus and is just learning the MVT and the IVT. All right, this is bad news for you. Okay, now the patrolman's going to rewrite your ticket and is going to charge you twice for driving 65 miles per hour. How can he prove this? All right, so now we just used the mean value theorem to prove that we were going 75 miles per hour at least once on that interval. Okay, so now we're going to combine that with our IVT. All right, so we are going to say that we're going to do T, we're going to make a table. T, and then I'm going to put speed right here. Okay, so I know at 0 minutes, we were going 50 miles per hour because they told us that we were clocked at 50. All right, and then 4 minutes later, we were going 50 again. All right, and then I know at some time, we'll call it C, in between the 0 and 4, we were going 75 miles per hour. Then I'm going to put from part A. Right there, just to tell the person reading my work that that's where I got that number from. All right, and so now we can apply the intermediate value theorem. Okay, so for intermediate value theorem, we need a speed. Speed is the function we're looking at now. So I was saying speed over here, and I realized I was wrong, and I should have said distance. Well, down here, speed is correct. Since we're applying the intermediate value theorem to this particular function, we need to say that speed is continuous. That is all that you need for, that's the only condition you need to be true before you start doing some work with the intermediate value theorem. So speed is continuous. All right, so number 2, we have to do our inequalities. So I'm going to say, let me give speed a function name. I'm going to call it v of t. Velocity, we use that for speed a lot. Okay, so I'm going to say that v of 0 is equal to 50, which is less than or equal to 65, which is less than or equal to 75, which is equal to v of c. So there's once, and then v of 4 is equal to 50, less than or equal to 65, which is less than or equal to 75, which is equal to v of c. And that's it. Therefore, IVT applies. Then I'll add a little extra here just because usually when we do IVT, we're just proving one location, and this time we used it to prove 2 locations. So I'll say, therefore, IVT applies, and we must have been, driving 65 miles per hour 2 different times. All right, so there's kind of a nice little real-world example that shows you how MVT can work and how they can include IVT. There's definitely been a free response question. Been a few years from now, I'd have to look up the exact year, but there's one that involved this, where you had to do an MVT on one part of the question and you found your value, and then you had to use that on the second part or on the next part with the intermediate value theorem to identify a different value that's in between the one you found. Okay, so I really like this one because it kind of connects a little bit of everything with the theorems we've done so far. All right, hopefully you enjoyed that as well, and I'll see you for the next video.